Okay, welcome back. Let's look at this other theorem. In the diagram below, O is the center of the circle passing through A, B, and C. EA is a tangent. Remember the definition of a tangent. What is a tangent? It's a line that touches a circle at a point to the circle at A. That's a point of contact. In the diagram, use the diagram to prove the theorem that states that EAC is equals to ABC. What does the theorem say? Says that the angle between the tangent and the chord is equal to the angle sum by the same chord on the opposite segment. Now, usually we call it a tan-chord theorem. So, which I can say to you now that now this is tan-chord theorem. Between this tan and chord, you can see there's a dash or there's a space. Now, let's use that space to put an angle. To say now this means an angle. So I will say the angle between the tangent and the chord. Yes, that's how you can say it. The angle between the tangent and the chord is equal to the angle subtended by the same chord on the opposite segment. Remember again, this is our RTP required to prove that this angle here, because it's between this chord and this tangent. So it's between them. And now this chord here subtended this angle here. But how do we know that the angle has been subtended? When you put your fingers at A and at C, we go with the lines, then our fingers end up at B. So B, this angle will be between the two fingers here. That's how we know that the angle has been subtended. We'll do more activities to see how these angles are subtended. So now let's go to the construction. We know that to prove a theorem, we need to construct something. Now we construct, what do we construct here? We construct a diameter. We construct a diameter. Let's call it a diameter DOA. So that means I'm going to put my D here. Then construct the diameter. I'm going to put my D there and construct my diameter going down here, passing through the center. That is diameter and join. Now, because I want to prove B, listen carefully. I want to prove B. So I oppose the opposite of B. Here I have B and C, the points which are not in contact with the tangent. So I'm going to join my C here. I join C and join C. That's what I've done. Now, there's a critical angle here. This is the critical angle. Everything that we do lingers around this angle. So let's name this angle here. This angle is formed from D to A, then to C. We're talking about angle DAC. That's the critical angle. Everything we do, we must talk about this angle. Now, where do we see this angle? This angle is inside a triangle ACD. And we draw the diameter here. We know that diameter subtend what? 90 degrees. We've done it. Diameter subtend 90 degrees already inside the triangle. In this triangle, we already removed 90 because we know that sum of angles in the triangle add up to 180, meaning that the two remaining angles should give us 90. Then the remaining angles we have angle D, and the angle that I said is very much critical. So we're gonna say that angle D, it is equals to 90 minus the angle which is critical, which is DAC. The reason for that, we write sum of angles in a triangle add up to 180 degrees. Now, even though we said 90, because I've explained that this is 90 here, because of the diameter 90 degrees. Now we've removed it. Now we come back to another story. We know that diameter is always perpendicular to the tangent. Diameter always perpendicular to the tangent. Now again, the angle that we talked about there, it is there. DAC, it's inside here. So we're just going to pick up the angle here. The angle that we have here is CAE. It is equals to 90 minus DAC, the critical angle. That is it's very important. The reason I've already mentioned, tan perpendicular to a diameter or a radius, because diameter and radius usually are the same thing, or their diameter and radius are the same thing. Now we're looking at this. Now we're saying if you look at this side, we have 90 minus DAC. 90 minus DAC, which now bring us to say angle D, it is equals to CAE. the reason for them to be equal, we can say because both are equals to 90 minus DAC. Now, looking at that, that's fine. Now, let's look at angle D. How is D connected to B? If you look at AC, if I put my fingers at A and at C, like I've mentioned, they go to B. I put my fingers at A and B and C, they go up to this D here. So these are on the same segment or angles subtended by the same chord. So that means I can say my angle D, it is equals to that angle ABC. That is, those are angles on the same segment. So they are on the same segment, those angles. Now look at this. I have D. Therefore, if this D is D, these are such. If what's on the right is equal, what's on the left must be equal also. So I'm going to say that now. This means that my CAE, it is equals to ABC. Then that's the theorem. Why are they equal? Because they are both equals to D.